You know that magic moment when a high-end robotic arm moves with, like, absolute pinpoint precision? It looks like the software is just thinking, and the metal is effortlessly obeying.
Yeah, but under the hood, that code is entirely at the mercy of brutal, unforgiving mechanics.
Right.
If the physical hardware can't perfectly translate those digital commands, I mean, the whole illusion just shatters.
So today we're tearing down the mechanical rules that make that translation possible. We're looking at a technical visual glossary from 2026 on precision transmission and exploring how 5 critical engineering parameters physically dictate what a robotic system can and cannot do.
It's a really fascinating look at how software isn't actually in charge. Physics is.
Yeah, physics always wins.
Yeah.
So let's start at the very point of contact, right? The gear teeth themselves, there's this term involute. And before reading these specs, I just pictured gear teeth, mashing together.
Right, like building blocks.
Exactly. But an involute curve is much more dynamic. It's less like 2 interlocking bricks and more like relay runners passing a baton at a full sprint. The contact point rolls smoothly along the curve without any slipping or scraping.
And that rolling contact is the entire secret. Because in real-world manufacturing, the center distance between 2 gears is just never absolutely flawless.
There's always some margin of error.
Exactly. There's always microscopic deviations. So the involute profile guarantees that even if those gears are slightly further apart than intended, the transmission ratio stays mathematically constant. You don't get any jerking or binding up.
Wow, just perfectly smooth power. But, I mean, perfectly shaped gears don't matter if the whole assembly rips itself right off the robot arm when it moves, right?
Oh, absolutely. Which brings us to the actual physical integration. You have to secure that incredible force.
Yeah.
The engineering specs strictly govern the mounting pattern, which dictates how the gearbox connects to the output flange. That's basically the heavy-duty metal mounting plate that attaches to the load.
And the specs mention this relies on the hole count and the PCD, or pitch circle diameter. So are we talking about an imaginary circle drawn straight through the center of all those gear teeth to map exactly where the bolts have to go?
Precisely. In mechanical design, if that mounting pattern is miscalculated by even a fraction of a millimeter, well, the physical structure simply shears under load.
Ouch. Okay, so the gears are shaped perfectly, and the casing is bolted down tight. Now we tell it to move, and this seems obvious, but the control software actually has to verify the direction of rotation.
Yeah, it's critical.
Wait, if I tell a motor to spin clockwise, doesn't the output just naturally spin clockwise?
Well, not necessarily. It depends entirely on the internal gearing. Take a single-stage planetary gearbox, for example.
That's the one with a central sun gear surrounded by orbiting planet gears, right?
You got it. The technical callouts explicitly note that in this specific setup, the input and output spin in the exact same direction. They're co-directional.
So if the software assumes a different gear arrangement where the rotation naturally flips, the robot arm swings left instead of right and, I don't know, smashes into a wall.
Exactly. The software engineers have to map their code directly to that mechanical reality.
Okay, let's unpack the speed, though. Because modern motors are insanely powerful. Why can't we just push them to their absolute physical limits?
That's a really common question.
I mean, the specs list a strict rated input speed, but honestly, why cap it? Why not just let the motor fly?
Because physics always extracts a toll, and in this case, the toll is friction. If you push a motor past the gearbox's rated input speed, you generate massive amounts of heat.
And heat is bad news for gears.
It is, but it directly attacks the system's weakest links first, which are the oil seals. The rubber lip of the seal literally fractures, or the internal tension spring fails.
Oh, wow. So you push the speed, you melt the defenses, oil leaks out, and the system grinds to a halt.
Exactly. And since friction generates heat internally, that makes the environment outside the gearbox just as critical.
Right, which explains the strict rules around operating temperature. If a robotics team deploys one of these systems in an extreme outdoor environment, like, say, an Arctic pipeline or a desert solar farm, they aren't just looking at the weather.
No, not at all. The external temperature physically dictates the internal chemistry of the machine.
So it's about the materials.
Exactly. The operating temperature range forces engineers to select highly specific, specialized rubber for those seals, and it dictates exactly which synthetic lubricants can actually survive inside the casing without freezing solid or boiling off.
It really shows how deeply interlocked all these parameters are. You start with a mathematical curve of a single gear tooth, and you end up balancing the chemical properties of oil against the weather outside.
Yeah, hardware really is the ultimate reality check for software.
It really is.
Hmm.
But as we move toward AI-driven robotic systems that continuously adapt their own performance in real time, it makes you wonder about the future.
Oh, for sure.
Like, how will engineering teams need to redefine rigid static parameters like rated input speed? Will we ever see hardware that can dynamically shift its own physical limits based on what the AI wants to do?
Yeah.
Just something to mull over next time you see a robot in action.